Which of the following represents the most stable conformation of cis-1-ethyl 4-methyl cyclohexane? So when we're looking at a most stable conformation for a cyclohexane, we should automatically be thinking about a chair conformation. So we want to definitely have a chair conformation. And then the second thing we want to recognize is where the substituents are. So ideally, we want to make sure that our largest substituents are on equatorial bonds. We want to make sure our largest substituents are equatorial. If we can come up with a structure where all of the substituents are equatorial, that would be fantastic. But we are constrained by the stereochemistry that we're given. We are told that this is cis, which means they have to point in the same direction. So the best strategy to take here is to decide which of your substituents is the largest, put it on an equatorial bond, find the next position, and place your smaller substituent relative to the first. If it's cis, you're going to put it in the same direction. If it's trans, you're going to put it pointing in the opposite direction. So I would draw a cyclohexane chair. And then I would pick any carbon and put that larger group, which would be the ethyl group, is the larger group, 2 carbon atoms versus 1 carbon atom. And so I'm going to place that on an equatorial bond. So you can technically place that anywhere along the ring. I find it the easiest to draw off of the end carbons just because these get a little crowded. So if I can, I usually start there, but it really doesn't matter. Any equatorial position will work. So if I say I want to start at this carbon atom, I should recognize that the vertice here is pointing up. So that means the axial bond is up. I want the equatorial bond. That means that equatorial bond is angled down. So there it is. And so that's 1 carbon atom. If it's an ethyl group, I need a 2nd carbon atom. So I have made this carbon number 1, and this bond is pointing down. So for this to be cis, I need to go to the position where my next substituent is going to be, which is carbon 4, and I need to place the methyl group on the down bond of carbon 4, whether it is axial or equatorial. So 1, 2, 3, 4. If I count the other way, 1, 2, 3, 4. No matter what, I get to the same carbon atom. And the vertice here is pointing down. So that means the axial position is the down bond here. And so although I'd prefer this to be equatorial, if it's cis, it has to be pointing down. So this is the most stable conformation for this cis-1-ethyl 4-methyl cyclohexane. So this is also pointing down. So I want to just examine my options and see which one that is. And so this looks like A. Actually, it looks identical to A. If we look at B, just to run through these options quickly, this is down and this is up. And this is a dimethyl. So this molecule here is actually trans because one is up, one is down. 1,4-dimethyl cyclohexane. So that is actually not even the right molecule. So although we see these 2 equatorial groups and it's stable, it doesn't apply because it's not the one we're looking for. If we look at C, we have an ethyl group pointing up, and we have a methyl group pointing up. So this is the other chair conformation of that cis-1-ethyl 4-methyl cyclohexane. So this is the right molecule, but it has, so cis-1-ethyl 4-methyl cyclohexane, but it has the larger substituent axial, and that is not what we want. So having the larger substituent equatorial is what we were looking for. And if we want to look at this very last one, we have a methyl group pointing up and we have a methyl group pointing or an ethyl group pointing down. So this is the trans isomer of this molecule. This is trans 1-ethyl 4-methyl cyclohexane. So what we're seeing here is the trans isomer should be lower in energy than the cis isomer overall because you can get both of those groups equatorial, but we weren't asked for the most stable of any 1-ethyl 4-methyl cyclohexane. We were told we were looking for cis, so that's why A is the right answer.